Welcome to Study Loop.
Hi everyone, thanks for joining me today. What we're going to be looking at is a problem with centripetal motion and work and kinetic energy. So what we have is a mass that is swinging about a rope of length L, of radius L, and it is given a velocity at point A when it is flung. So let's actually go ahead and actually write that down as also part of our given information. And what we're asked to solve for is the angle at which the rope breaks, knowing that it breaks when the tension is equal to 2 times the weight. So what we're going to do is going to draw a free body diagram for this mass at a point theta. So here's the mass shown here. Here is the force due to tension, and here's the force due to the weight. This is the angle theta. And for our coordinate systems, we're going to choose a normal and tangential coordinate system. So here's the tangential and here's the normal, just because we're dealing with circular motion. So as we break these forces down and write out Newton's second law, we will find that, here's the weight and tension, we'll find that the tension and a component of the weight force is what act in the normal direction, and we'll find that tension minus weight sine theta is going to be equal to ma, which for circular motion is mv squared over L. And now what we're going to do is we're going to invoke our energy principles. So we know that the ball or the mass is given some energy when it is thrown at A. So we know that T1 will be 1/2 m v naught squared, and it'll have some velocity when the rope breaks, so that's going to be that T2 is going to equal 1/2 mv final squared. And then we know that the work done throughout this motion is solely due to gravity, and that's going to be equal to mgh. Now remember, h we can write in terms of the length, and we can draw a simple triangle here where this is L, this is theta, and this will be h1, this will be h2, and this distance is simply L sine theta. So we can say from here that u from 1 to 2 is mgl sine theta. So moving forward, looking at our energy equation relating kinetic energy and work, we know that T1 plus u from 1 to 2 is equal to T2. So knowing what we have here, we can say that T1 is 1/2 mv naught squared plus u12, which remember is mgl sine theta, is going to be equal to 1/2 m v final squared. Now, we don't know what v final squared is explicitly, but we do know it in terms of the centripetal motion. Remember, because we have an expression for v final squared within this Newton's second law. Now, we're also going to assume that the rope has broken, because that's what we're asked to solve for. So we're going to assume that tension is equal to 2 times the weight. Remember, that is a condition that was given to us in the beginning. So, solving for Vf squared and knowing that, this is in play, that the tension is equal to 2 times the weight, we see that the Vf squared will be equal to 2 times the weight times L minus W L sine theta all over the mass. Now luckily, we don't need to know the mass because mass will simplify out in the weight, so we can get VF squared equals 2GL minus GL sine theta. So plugging this quantity in for our expression here for BF, we get an expression that looks like this. We have 1/2 mv0 squared plus mgl sine theta equals 1/2 mgl, 1/2 2gl minus this down here, gl sine theta. I'm going to continue. And we can see here that our masses cancel out, which is great. Makes computation a little easier. And what we're going to do is multiply the whole thing through by 2 just to get all the fractions out of there. And what we're going to end up with is v0 squared plus 2gl sine theta is equal to 2gl minus gl sine theta. Again, we're going to combine like terms, so we're just going to bring all the sine theta to one side. So we have 3gl sine theta equals 2gl minus v0 squared. Now if we solve for sine theta, we get sine theta equals 2gl minus v0 squared all over 3gl. By taking the inverse of both sides, we get that theta is equal to 14 degrees. And that is our final answer.